Imagine a machine so powerful that it solves a problem in minutes. One that would take the world's fastest supercomputers longer than the age of the universe to complete. It sounds like science fiction. Yet in late 2024, Google unveiled a quantum processor called Willow, and its performance immediately sparked one of the biggest discussions in modern science. At first glance, Willow doesn't look extraordinary. There are no giant spinning mechanisms. No futuristic glowing engines. Instead, it sits inside an ultra-cold chamber, cooled to temperatures even colder than deep space itself. Within that frozen environment, something remarkable occurs. Unlike classical computers, which process information using bits that exist as either 0 or 1, Willow uses quantum bits, or qubits. A qubit can exist in multiple states at the same time through a phenomenon known as superposition. This means the machine isn't limited to exploring one solution after another. It can examine many possibilities simultaneously. When multiple qubits become entangled, they form a deeply connected quantum system. Changes to one qubit become linked to the behavior of others, creating patterns that classical computers simply cannot reproduce efficiently. This is where quantum computation begins to feel almost alien. Rather than following a single path toward an answer, the system evolves through a vast landscape of possibilities. Some possibilities strengthen. Others cancel each other out. The final result emerges from an intricate process called quantum interference. And according to Google's benchmark tests, Willow performed a calculation in only a few minutes that would require an impossibly long time for traditional supercomputers to reproduce. The exact benchmark wasn't designed to solve practical real-world problems. Instead, it was created to push quantum systems into regions where classical simulation becomes extraordinarily difficult. The result demonstrated something important. Quantum computation is not merely faster computing. It represents an entirely different way of processing information. But this achievement raises a deeper question. What is actually happening during a quantum computation? Physicists have debated this for decades. One interpretation suggests that quantum systems don't choose a single outcome until measurement occurs. Instead, every possible outcome exists within the quantum wave function. Among the most famous explanations is the many worlds interpretation, originally proposed by physicist Hugh Everett. According to this idea, quantum events do not collapse into one reality. Every possible outcome continues in its own branching version of reality. Most scientists remain cautious about taking this interpretation literally. Yet quantum computing has made the discussion difficult to ignore. Why? Because machines like Willow appear to access computational resources that classical systems cannot efficiently imitate. Physicist David Deutsch famously suggested that quantum computers may be understandable as systems that exploit the full structure of quantum reality. Not by communicating with parallel universes. Not by opening portals. But by operating within mathematical rules that include all possible outcomes simultaneously. Whether that interpretation is correct remains unknown. However, Willow's performance highlights something undeniable. Nature itself appears capable of processing information in ways that exceed classical intuition. For centuries, humanity viewed reality as something predictable and sequential. Cause followed effect. One event led directly to another. Quantum mechanics shattered that certainty. At the smallest scales, reality behaves according to probabilities rather than certainties. And quantum computers are the first machines designed to work directly within that strange realm. The significance of Willow is not that it proves parallel universes. The significance is that it forces us to reconsider what computation actually means. Perhaps computing is not merely the manipulation of information. Perhaps it is something deeply connected to the fundamental structure of reality itself. And if that is true, then Willow may represent the beginning of a technological revolution unlike anything humanity has experienced before. The most impressive aspect of Google's Willow chip may not be its speed. It may be its stability. For decades, one of the greatest challenges in quantum computing has been error correction. Quantum systems are incredibly fragile. A tiny vibration, a small temperature fluctuation, even a stray electromagnetic disturbance. Any of these can disrupt a qubit and destroy the delicate quantum information it contains. As quantum computers become larger, errors typically increase. This has long been one of the biggest obstacles preventing practical quantum machines. But Willow demonstrated something unexpected. As Google's researchers expanded the system and improved its architecture, error rates actually decreased under specific conditions. This may sound like a technical detail, but its implications are enormous. For years, many scientists worried that large-scale quantum computing might be fundamentally impossible. The complexity of maintaining coherence appeared overwhelming. Willow suggests otherwise. It indicates that larger quantum systems may become more stable through sophisticated error correction techniques. If this trend continues, quantum computing could move beyond laboratory experiments and become a transformative technology. But the implications extend far beyond engineering. To understand why, we need to look at what quantum systems are actually doing. Before a measurement occurs, a quantum state exists in a superposition of possibilities. Multiple outcomes remain available simultaneously. Only when observation takes place does a definite result emerge. This isn't philosophy. It's one of the core principles of quantum mechanics. And quantum computers depend entirely on this behavior. Their power comes from maintaining those possibilities long enough for interference and entanglement to produce useful results. In a sense, quantum computation occurs before reality settles on a final answer. That idea can feel unsettling, because it challenges the way we normally think about existence. We tend to imagine reality as a sequence of fixed events unfolding through time. Quantum mechanics suggests something different. It suggests that possibilities may be just as fundamental as outcomes. Machines like Willow operate directly within that domain. This is why some physicists argue that quantum computers are more than advanced calculators. They are physical systems exploiting the deepest rules of nature. Again, this does not mean Willow is communicating with alternate universes. There is no evidence for portals, messages, or interactions with parallel Earths. Those ideas belong to science fiction. Yet the machine still reveals something profound. It demonstrates that information, probability, and physical reality are intertwined in ways we are only beginning to understand. Every successful quantum computation reminds us that the universe behaves differently than our everyday experience suggests. The world we observe may simply be one outcome emerging from a far richer landscape of possibilities. Whether that landscape is literal, mathematical, or merely interpretive remains one of science's greatest mysteries. What we do know is that Willow has brought these questions into sharper focus. It stands as evidence that quantum mechanics is not merely a theory describing microscopic particles. It is a framework capable of performing computations beyond the reach of classical machines. And that realization may ultimately change how humanity understands reality itself. The most fascinating conclusion is not that Willow discovered parallel universes. It is that the line between information and reality may be far thinner than we once believed. As quantum technology advances, we may uncover answers to questions that have existed since the birth of modern physics. What is reality? What is information? And are they, perhaps, two different expressions of the same underlying truth? Willow has not solved those mysteries, but it has brought us closer to them than ever before.